Hi, everyone. Thank you for joining today's webinar on infrastructure readiness for automated vehicles. Really appreciate your attendance today. We're going to get started in just a moment. We'll give folks some time to come into the room. All right. So once again, it's great to have everybody for this webinar on infrastructure readiness for automated vehicles. My name is Adam Hops. I'm with the National Operations Center of Excellence. This webinar is hosted by NOCoE, but it's featuring the research of the fine folks that you see up on your screen from the University of Cincinnati, Kimley Horn, and Cambridge Systematics. Before I turn it over to Samantha Anderson to introduce our speakers and discuss the project, just a quick reminder, this webinar is being recorded. A recording will be made available and shared on our YouTube channel. The best way to get that recording is to sign up for the NOCoE newsletter. That's how our recordings are released. So if you haven't done that, please do so. I will put that into the chat box. We will be taking questions via the Q&A box. You can find that on your Zoom toolbar. Those questions will be moderated and answered at the end. We also have a webinar chat for people to sign in and say greetings, like some of you have started doing already. Or if you have any logistical issues, please use that to get a hold of me quickly. Lastly, we have a transcription and closed caption option as well that's in the Zoom box. Feel free to click on that if that's your preferred method. Once again, the recording of the presentations will be shared. Please look out for that and feel free to share it with your colleagues. So now I will turn it over to Samantha Anderson to introduce our speakers. Thank you so much.
Thanks, Adam. And thank you all for joining today's NOCoE-hosted webinar. I'm excited because today we'll be discussing an ongoing NCHRP research project, which is focused on developing practical infrastructure recommendations to help infrastructure owner-operators enhance their readiness for automated vehicles. All right, so I'm Samantha Anderson. I am a transportation analyst at Kimley Horn, and I've been heavily involved as a research analyst for this project. Doug Getman was unable to make the presentation today, but he is the principal investigator and is the main point of contact for this project. And I'm also joined by 3 other members from our team, and I'll let them introduce themselves. So Katie.
Hi, everyone. I'm Katie Piskai with Cambridge Systematics. I've been supporting the outreach for this project. I'm a senior associate in operations and technology planning.
Hi, everyone. I'm Munir Nazzal. I'm a professor of civil engineering at the University of Cincinnati. I'm also a director of Center for Smart, Sustainable, and Resilient Infrastructure.
Mohammed Ahmed, transportation professor of transportation engineering and department head of civil and architecture engineering and construction management at the University of Cincinnati. I'm leading human factor research for this project.
Awesome, thank you. All right, so here's a quick overview of what we'll cover today. We'll start by giving a project overview and some important background information, and then we'll dive into some of the key findings from our foundational research. After that, we'll walk through some of the infrastructure recommendations that we've developed based on that foundational research. And then the University of Cincinnati will walk us through the case studies that they've been conducting in the field and with their driving simulator. And then finally, we'll give you a preview of the web-based resource that we're building to help support the implementation of our guidebook. All right, so starting with a project overview. So this project really started with one central question. How does the physical infrastructure influence the operational design domain of driving automation systems? So our objective throughout this project was to develop recommendations for infrastructure maintenance and design that could help infrastructure owner-operators or IOOs that were seeking to prepare and support AV deployments. So our recommendations primarily focus on the physical infrastructure elements, but we also touch a bit on digital infrastructure where we find it relevant. So this is a 3-year research initiative, and it's scheduled to conclude in November of 2026. So with that being said, we're a little bit more than halfway done with the project. So we've completed phase 1 and are currently in phase 2. So as a part of this phase, we're collaborating with Dr. Ahmed and Dr. Nazal, who are conducting both the field testing and driving simulator case studies. And then we've also been actively sharing our research at conferences and webinars like we're doing today to help circulate awareness of this resource that we're developing. So the purpose of our work in phase 2 is to gain some valuable insights so we can refine and validate our infrastructure recommendations, which will ultimately feed into our revised AV infrastructure guide. All right, and now I'll pass it off to Katie to dig into some important background information.
All right, so first we want to set the stage with some background on how automated driving systems work and how infrastructure plays a role. So the dynamic driving task, or DDT, refers to real-time operational and tactical functions involved in vehicle control. And here we can see some examples of operational functions and tactical functions. Automation of parts of the DDT is what enables automation systems. Driving automation systems are classified into levels of driving automation, which many are probably familiar with. These define the division of responsibility between the automated system and the human driver. The levels range from level 0, where the human is fully in control, to level 5, where the vehicle handles all driving tasks under all conditions. And we can categorize these levels into two main groups. We have advanced driver assistance systems, or ADAS, for the lower levels of automation, and automated driving systems, or ADS, for the higher levels of automation. And every driving automation system, whether it's ADAS or ADS, has an operational design domain, or ODD. The ODD defines the specific conditions under which a given driving automation system is designed to operate safely. ODD requirements may include factors such as road type, surface conditions, speed, lighting conditions, and weather. It's important to note that the ODD is defined by the vehicle manufacturer or technology provider. So the exact ODD of, for example, a lane keep assist may differ slightly between manufacturers, but there are going to be many consistencies between similar applications. So for something like a lane keep assist, most ODDs would include clearly visible lane markings, and the visibility of the lane markings could be influenced by several factors, such as the lane markings themselves, road surface quality, lighting conditions, etc. And last slide in the background, beyond automation, connectivity plays a really important role in AV readiness planning. So connected vehicle, or CV technology, allows vehicles, bicyclists, pedestrians, and infrastructure to communicate in real time. So for example, digital infrastructure such as a roadside unit or RSU in a work zone might broadcast a lane closure alert. And this alert could be received by a human driver who would adjust their behavior, or by the driving automation system, which would incorporate that information into its decision making. So connectivity adds this extra layer of intelligence to the driving task by providing contextual awareness that the sensor would not otherwise have. Okay, so moving into the project itself, to build a strong foundation for our recommendations, the project began with an extensive literature review. So this covered academic research, federal studies, and regulatory guidance. And this literature review revealed 6 core categories of physical infrastructure that have a direct influence on the ODD of AV systems. And you can see these on the right side. These are pavement markings, roadway surface, traffic signs, traffic signals, temporary traffic control or work zones, and geometric design. And so what we found in the literature was that inconsistencies in the design, placement, or maintenance of these elements can significantly limit the vehicle's ODD. And then when these inconsistencies exist in unpredictable conditions like a work zone or a school zone, it presents an added layer of challenges for the AVs. And then next, shifting into digital infrastructure. Digital infrastructure is considered an enabling technology, and it can help AVs overcome challenges tied to physical infrastructure and operate in more complex driving conditions. So it provides that critical context beyond what the onboard sensors can detect. And we looked at several aspects of digital infrastructure, and those are shown on the right side of the screen. Something that stood out is that ITS deployments are increasingly used as a readiness metric when evaluating how prepared an area is to support CV-enabled infrastructure. And then finally, while the literature was a really important starting point, it came with some clear limitations. First, because much of the AV industry is for profit, there's a disincentive to publish deficiencies with AV technology. And as a result, there were limited reports on disengagements and control algorithm errors, especially in complex environments. And finally, most of the published studies that were available were conducted in academic settings. And these often will use non-production grade AV systems and tools, and they may not fully reflect what is happening in the real world deployments. And now I'm going to hand it back to Samantha to talk about some AV industry feedback.
All right, thanks, Katie. So we've covered what literature tells us, but as Katie discussed, there are still gaps in the literature, especially when it comes to those real world deployments. So to help fill those gaps, we engaged directly with the AV industry stakeholders. So that included developers, manufacturers, and testbed operators. So this next section summarizes the key themes and concerns that we heard from those conversations, and then how that feedback helped shape our recommendations moving forward. So some common themes that we heard included the need for uniform infrastructure across markings, signs, and signals. And when consistent and uniform infrastructure is lacking, HD maps are a critical tool that can help the AVs overcome some of these infrastructure gaps. We also heard that AVs struggle most with unpredictable road users, especially in ambiguous situations that can be caused by degraded infrastructure. You could go to the next point, and the next one. They also talked a lot about the shared benefits, so the infrastructure improvements that support AVs also enhance the safety and the clarity for the human drivers. And then finally, to spur the safe adoption of AVs, it's essential to educate both the public on these systems' capabilities as well as their limitations. All right, so moving on to some common key infrastructure investments that we heard from these conversations. So within the realm of physical infrastructure, we heard that pavement markings should be highly visible and applied consistently across jurisdictions. So that includes ensuring a proper contrast, color, pattern, and design. We also heard that there's a need for better separation and channelization of the non-motorized road users, especially in urban areas. And improved sight distance is especially critical at permissive and complex intersections where AVs may need to rely on more visual input in order to make decisions. And safe harbor locations, also known as shouldering areas on highways, provide critical fallback zones for AVs when these disengagements occur. Now, looking to the digital side, the industry is looking for real-time information about work zones, crashes, and special events, all centralized through an API like the Work Zone Data Exchange or Cellular Vehicle to Everything. They also emphasize the need for emergency vehicle data, as the presence and routing information can help AVs respond appropriately in these scenarios. And then finally, AVs benefit from access to real-time signal phase and timing information to help improve their navigation and reduce risk at intersections. So now that we've explored the challenges and insights from both research and the AV industry, we can shift into the core of our project, which is really our infrastructure recommendations guidebook. So these recommendations are organized by infrastructure category based on what we found to have the biggest influence on AV's ODD. So these recommendations are split into 8 different categories that are shown on the screen. So it includes various elements of the physical infrastructure, as well as digital infrastructure, and then different policies and procedures that are important to consider. So today we'll mainly focus on the physical infrastructure recommendations, since these will feed directly into the case studies that Dr. Ahmed and Dr. Nizal will be presenting on later. So starting with recommendations for pavement markings, FHWA identified these as the top IOO investment to help broaden AV's operational design domain, or their ODD. So well-maintained pavement markings support both level 1 and level 2 ADAS that heavily rely on their camera perception algorithms, but they also help support the level 4 fleets, which are mainly using their HD maps, but still relying on markings to help with the real-time lane validation. So given their importance, it's not just about having the pavement markings in place, It's also about maintaining their quality and their consistency over time. And while standards for implementing these markings are established in the MUTCD, there's still a growing need for stronger asset management practices to help ensure that these markings are remaining uniform and high performing across the network. So from an AV's perspective, research points to two primary factors that are influencing how well these markings are detected. So that includes contrast and retroreflectivity. Contrast appears to be one of the most important measures for machine vision detection, with studies suggesting a minimum contrast ratio of 3:1 for reliable lane recognition. Retroreflectivity also plays a major role, especially in the low light and wet conditions. Literature indicates that a minimum value of 150 millicandelas per square meter per lux is needed for this consistent detection. Now, pavement marking design can also help AV systems better detect the lane markings. So wider 6-inch longitudinal markings give AV cameras a larger and higher contrast target, essentially providing more pixels for their detection. The National Committee on Uniform Traffic Control Devices recommended updates to the MUTCD based on their research on incorporating ADS systems into highways. So they recommended the use of 6-inch markings on all freeways, expressways, and ramps, as well as on all of their roadways with speed limits greater than 40 miles per hour. And they also recommended the use of 6-inch edge lines for all 2-lane roadways. When raised pavement markings or RPMs are used alone, or if they aren't maintained, they can actually hinder machine vision from reliably detecting the lane markings. So it's recommended here that RPMs are only used as a supplement to the painted markings, and they shouldn't actually replace them. So that means that non-reflective RPMs, sometimes referred to as box dots, also shouldn't be used as a standalone lane delineation method. Level 1 and Level 2 ADAS systems like Lane Keep Assist rely heavily on their vision-based perception algorithms to help identify lane boundaries and maintain lane positioning. So when pavement markings are missing for more than a few seconds at normal driving speeds, the vision-based system may be forced to disengage. So sometimes access controlled facilities, which are the most common operating environments for the Level 1 and Level 2 ADAS systems, will sometimes lack these lane-specific markings, especially at ramps, diverge points, and in merge areas. So to improve reliability in these locations, it's important to include dotted line extensions along all entrance and exit ramps, as well as on aux lanes. And chevron markings within gore areas are important to clearly help distinguish the exit lane from the travel lane. Now, similar to access control facilities, missing pavement markings in complex driving environments like intersections can significantly limit the effectiveness of AV technology. Most Level 1 and Level 2 ADAS systems aren't designed to operate in these environments, so this recommendation is really impacting the Level 3 and Level 4 ADS deployments. So when navigating an intersection, dotted edge line extensions provide crucial wayfinding points for these vehicles. And this is especially beneficial for intersections with more than one turning lane, those with unique geometry, or sharp turning radius. Now, representatives from the AV industry also recommended that pedestrian crosswalks, bike lanes, and bus lanes be distinctly marked to enhance their visibility. So by using colored pavement markings, this can help distinguish these areas from the regular traffic lanes. All right, so moving on, there are various roadway surface characteristics that can influence the performance of machine vision algorithms. So this includes the use of, next slide, pavement crack sealers, which can appear similar to the lane lines, especially to ADAS technologies like Lane Keep Assist. So the best practice here is to select crack sealing materials that blend in with the pavement and are easily distinguishable from the lane markings. With regards to potholes, we noticed that in our field testing, Level 3 Teslas didn't consistently slow down when they encountered a pothole. So in some cases, that can lead to steering issues, especially on some high-speed corridors. The best practice here is to implement a proactive pothole management program that includes regular monitoring and prompt repairs, especially on these high-speed corridors. Moving on to traffic signs. AVs rely on 2 layers of machine vision algorithms to really interpret traffic signs in real time. So this first layer is a detection algorithm. It will scan the roadway and then flag any object that looks like a sign. And then once that happens, a second layer, which is the classification algorithm, will then review the detected image and determine what type of sign it is. So this two-step process will allow for AVs to quickly react to signage, but it also means accuracy depends heavily on the consistency of what the system is seeing in the environment. So machine vision systems rely on this template matching to compare features of a detected object to a database of known sign templates. So when sign colors, sizes, shapes, or symbols vary, or when non-standard or unique signs are used, the system may misclassify the signage. Sign visibility is also impacted by overcrowding or occlusion, which is typically more common in the dense urban environments, where sign visibility is more likely to be reduced. Now, proper sign placement is also important. So factors like height, lateral offset, and angle determine whether the system perceives the sign as applying to its current lane. So in the top left photo, for example, we see the AV misinterpret signage from a nearby frontage road as being an applicable road rule for the freeway. And when it comes to electronic and dynamic message signs, AV developers share that these present a unique set of challenges for the perception systems. So the biggest technical challenge is related to the sign's brightness and their refresh rates. So if a sign's refresh rate happens to synchronize with the vehicle camera shutter, the sign may appear blank or just unreadable to the system. Now, variable speed limit signs were also mentioned as a specific pain point, with difficulties distinguishing these signs as regulatory. And just like with standard signage, consistency in color, shape, size, and mounting position support better detection. Also, maintaining flicker rates greater than 200 Hertz can really help ensure that the AV cameras are reliably capturing and interpreting the displayed message. Now, crosswalk signage, like in pedestrian signs typically used in school zones, present some other unique detection challenges. So these signs are typically smaller, mounted lower to the ground, and often use smaller text and symbols. So that reduced size and height can make them less visible to AV perception systems. And then they're also more susceptible to occlusion. So being blocked by a vehicle up ahead can cause that occlusion, which makes it harder for the detection systems to consistently identify them. So the best practice here is to install crosswalk signage at standardized heights and in locations that really maximize their visibility to reduce that risk of occlusion. Now, as AVs become more common, dedicated infrastructure and signage for bicyclists will play an increasingly important role in ensuring safe interactions between all of the road users. And because bicyclist movements can be unpredictable, AVs rely on clear pavement markings and consistent signage to help their perception systems anticipate the merging, crossing, and yielding behaviors. To enhance safety, bike lane signage should be installed where a lane ends and merges with the general traffic, and advanced warning signs should be placed before that transition zone. And when we think about future methods for AVs to read roadway information, one concept that's been explored is the use of QR codes that could be detected exclusively by the machine vision systems. So AV industry representatives have expressed this interest, but have also emphasized that in order for these technologies to be effective, they really need to be deployed consistently and at a scale nationwide before the integration into their systems would be worthwhile for them. Now, similar to signage, AVs rely on two machine vision algorithms to detect and then classify the state of traffic signals for a specific lane. And the challenges and risks associated with an AV navigating an intersection is really dependent on the vehicle's trajectory, the infrastructure elements denoting the intersection, and the behavior of the other road users within or neighboring the intersection. So the ability of an AV to detect a traffic signal state is heavily influenced by their size and brightness of the signal head. Research and feedback from the industry suggests that 12-inch signal lenses are preferred over 8-inch ones because the larger diameter provides a more distinct and easily detectable light source for the onboard cameras. One AV industry representative also noted that LED signal heads are significantly easier for the perception systems to detect compared to older incandescent bulbs just because of their sharper light contrast. And signal head visibility can also be improved by using black or yellow backplates, especially in areas where overcrowding of other signals and signs may be an issue. And anything that reduces the visibility of a traffic signal increases the chance that an AV could misclassify its state. So traditionally, optical programming and mechanical louvers are used to control the viewing angles and reduce glare for human drivers. But for AVs, these same mechanisms can actually limit the field of view for the onboard cameras, making it harder for them to detect and correctly interpret signal indications. And because of that, the recommendation is to minimize the use of optical programming and louvers wherever it's possible. But if they're necessary, mechanical louvers are preferred since they typically allow for better signal visibility within a controlled angle. Flashing indications and beacons present interpretation challenges for AVs similar to the issues encountered with refresh rates of electronic signage. So for instance, RRFBs can be difficult for AVs to detect reliably because of their rapid flashing patterns and their inconsistent refresh rates. And in these scenarios, AVs must depend more heavily on their pedestrian detection systems and predictive algorithms to determine when to yield for pedestrians. So the best practice here is to use solid signal indications using standard colors like green, yellow, and red over flashing beacons wherever it's possible. Now, work zones present some of the most complex challenges for AVs because of their dynamic nature. Industry representatives have noted challenges in work zones extend across nearly every type of physical infrastructure, from pavement markings and traffic control devices to signage and barriers, all of which can sometimes differ from permanent roadway standards. So one of the most persistent challenges for AVs in work zones is their ghost markings. So to address this issue, several DOTs, including Kentucky, Wisconsin, California, Indiana, and Texas, have been piloting the use of orange pavement markings to help clearly distinguish temporary lanes in work zones. So a joint study conducted by Indiana and Purdue found that AV systems detected orange markings with 100% accuracy, which was comparable to standard white and yellow markings. The AV industry representatives have also expressed strong support for the strategy, noting that a contrasting color like orange can significantly improve lane detection, especially for long-term work zones. Kentucky's testing also showed that retroreflectivity standards for orange markings can be met when high-quality bead packages are used, making this both a practical and effective solution. Now, the presence of roadside workers presents a unique set of challenges for AVs in the work zones, especially when there's no physical protection like a concrete barrier separating them from the active travel lane. And because pedestrian intent can be hard to predict, workers moving near open lanes or between cones can cause a level 4 ADS system to slow down or even stop completely as a safety precaution. So wherever possible, workers should be physically separated from the roadway using barriers to help minimize these interactions. Also, V2X communication technologies can enhance safety by allowing AVs to detect and respond to workers more effectively. Some emerging tools use connected devices mounted on phones, light fixtures, and even workers' vests to transmit position data, helping to alert the AVs of nearby human activity and helping to prevent potential conflicts. All right, now I'm going to pass it over to Dr. Nazal, who's going to kick us off on some insights from our field testing case studies.
So thank you. Thank you, Sam. So our case studies basically focused on the studying. We have two case studies, and basically the one that I will be presenting today is focusing on the infrastructure elements. We wanted to answer one main question, which is how the different infrastructure elements basically affect the safe operation of autonomous vehicles. We had two main questions. There was a lot of focus, as you have seen, on pavement marking. And as a result, basically our first and main focus was to see how the pavement marking is affecting the safe operation, and also we wanted to see what are the properties and characteristics of the pavement marking that are needed to ensure safe operation of the AVs. The other important thing is that we wanted to see how different road surface distresses and properties can affect the AV operation. And here we focused on, I would say, two main things. The first is the pothole, which is very common distress in pavements. And then the other important thing is the crack sealant, which is a treatment to a very common distress, which is cracking. So we're trying to see if there is any impact and or how that the potholes and the crack sealant affect the safe operation of AVs. So to do this, we used actually different vehicles, but the focus here is really on a level 3 testing that we have done. And basically the test vehicle was a Tesla Model 3. We have operated it in a full self-driving. Basically, I'm showing the two versions used. Just to let you know, this experiment and the case study took place during the summer of 2024 all the way till basically winter of 2025. It was completed, I would say, by March of 2025. And the main reason why we have done that is that we wanted to make sure that our study covered basically summer, fall, as well as winter. And what we have there is basically we added and mounted a sensor system that was basically developed and designed for specifically for this study. And that system have several sensors to help us understand the different infrastructure elements and their properties. So we have a ouster LiDAR. We have two cameras, and basically one that you see here in your left, which was mounted on top, and that's focusing really on the road and road elements, including the pavement marking. And then we have another camera and the first camera, I would say that it had a high resolution images. The second camera was really only focusing on what the screen of your Tesla. And then we had a GPS IMU. All of those sensors basically enabled us to have a look at basically when there is a disengagement or there is a I would say a false detection, which we will be talking about it in a moment, or a non-detection. Then basically whenever we're having an issue or the vehicle is having an issue, we're documenting it and everything is being synchronized with the other data. So we did some, I would say, sensor fusion, which enabled us really to determine whenever we have a disengagement or a false or a detection or a non-detection. Basically, we will be able to see the properties of the infrastructure elements, the different infrastructure elements at that point. So the sensors, and just to give you an idea, if you can go to the next, please. This is basically the data that we have. Again, the frequency was 10 hertz for the LiDAR, the camera, both cameras, and the GPS, because we wanted to have a better location or an exact location. We had a 50 hertz. The LiDAR provided, of course, the point cloud, which included different things, but I think one of the most important things that we were looking into is the intensity. And then basically, as I said, there was one camera with a high resolution, and then basically we had another camera that was a lower resolution and focusing on basically the screen, the Tesla screen. One important thing that all those sensors were operated using a ROS operation system. So that enabled us basically to synchronize everything, all those sensors together. Yeah, if you can go next slide. So we did several routes. One important thing is that we did actually 10 routes, but then we ended up with selecting certain routes where we did most of our runs or all of our runs on those. Why we selected them? Basically, we wanted a route that represents a two-lane roadway, multi-lane roadway with different pavement marking. A poor, good, and no pavement marking were considered. We considered also a urban setting as well as a rural setting. We considered also places with good pavement condition and poor. And when I say good or poor in terms of having these stresses and focusing on whether we have a crack sealant or places with extensive crack sealant and other places without. This is basically an overview of the routes and basically the location that we have done those. One important thing is that we have driven those routes at different time of the day and different, I would say, dates, and we were focusing on the location of the sun with respect to the driver as well as the camera. We were also focusing on different weather, including wet, dry, as well as snowy days. We were focusing also on cloudy days as well as sunny days. And as I said, we were focusing on a different time of the year as well as a different time basically of the day, mainly focusing mainly that was important so that we can capture how the effect of the sun location will impact the driving. For every case, we did several runs. You can go to the next slide. So with all those, we focused on really three types of failures. The first is disengagement, and again, I will show a video for that. A false detection, which means that if you can go back, or yeah, that's fine. That's fine. We can go start with the first one. The disengagement. This is, as you can see, as we're driving, the disengagement is defined when basically the vehicle tells us that we need to take a control. So this is basically a point of disengagement. At that time, we were able to locate just before and just after basically that incident, what exactly the properties of the different infrastructure elements, and focusing here on the pavement marking quality. The next is basically another failure mode, if you can go to the next, please, is the false detection. And here, what I mean by false detection is that we have a solid center line, and it is being detected, as you can see here in the screen, the Tesla screen, as a skipped, which can be very dangerous. And basically that means that it might basically allow the vehicle to pass. The last type of failure that we noticed was the non-detection. So, and again, that's the focus was on the center line because that might be a basically a cause of an accident. And this is basically where you can see that the pavement marking is so faded and that the car see it at some times, but it does not see it most of the time. So basically we were able to determine that and do our analysis. So what we have done, if you can go to the next slide, is our approach is really looking at the entire data and focusing at those locations where we had the failure as we have defined. And basically what we have looked into is looking at characterizing basically the pavement marking and getting the properties that properties that can be used really to differentiate a pavement marking that might cause a failure to that might not. And basically we looked at the data. The first step was that we developed a model for detecting the pavement marking based on the images. And based on that, we did some analysis, color analysis specifically for the pavement marking. And again, we looked at places where there was a failure to places where there is no failure. And basically then we conducted a comprehensive statistical analysis to determine basically the threshold. We used 3 parameters. And if you can go to the next slide. Those 3 parameters is the Michelson contrast. It is basically based on a luminance or brightness contrast. Then we have another one, which is and again, this is how it was determined. We have also the CIE lab color distance. Again, this is more about the color difference, more than the brightness. And then the last is a RMS texture fragmentation. And basically, this is really detecting areas that might be you might have faded or no paint. And basically, this is about basically places where you are missing some of the paint there. So if you can go to the next slide. So what we have done through the comprehensive statistical analysis that we have done is we looked at basically for the different cases of this engagement, we looked at what are the properties of the center line marking as well as the edge line marking, and tried basically for the places where we have this engagement to see how those properties were different as compared basically to places where we did not have any disengagement. And again, this is based on multiple runs and multiple failures in that same area. And I would like to note one important thing is that those properties, if are based on the time of the day. So for sometimes we might have a disengagement, for example, during the morning, but then later in the afternoon or later in the morning, we might not have that disengagement. So basically, we because of our analysis, we were looking at how those properties are changing and linking it to the exact place where we have disengagement at that time of disengagement. And again, our system basically enabled us to capture that. And again, everything is synchronized. And with that, we were able to obtain basically for those sections at that time, what are the failure. And what we have noticed is that statistically, the properties where whenever we have a disengagement as compared to when we do not have this engagement, as you can see, this we can have different basically thresholds for this for different properties. Mainly here we were seeing that the color distance and Michelson contrast have basically were statistically significant, and basically we were able to get that optimal threshold of the delta E of 11, and here if it is 0.06, and again this is for a yellow pavement marking center line. If it is an edge line, we also notice that with those disengagement, basically we had the threshold was 6.6 and about 0.06 with a Michelin contrast, and again this is for the edge line. So those are thresholds that can enable the IOOs basically to make sure that their pavement marking, if they have a higher values, then basically this will indicate that they might not be susceptible or under the risk of having the AV disengagement. We go to the next slide. So this is for the false detection, and again this is focusing on center line marking, and this is for yellow center line marking, of course. Again, this is for 2-lane. In this case, we had the color distance, the delta E to be 9.8. Again, the Michelson contrast, it's to be 0.06, and then basically the RMS to be 0.14. Very important thing that all of those values, as you can see, are statistically significant at 95% confidence level. If you can go to the next. So the next is the non-detection. And what I mean by non-detection, basically, it is not detecting a yellow center line marking here. And basically, again, we have a color distance of around 10.6, and again, Michelson contrast of 0.03, and then basically an RMS texture of 0.22. And again, those are the values basically that the threshold that in our next slide that we'll be talking about it, if you can go back just 1 second, we will see that those were all those cases were gathered to basically to make a final recommendation for the infrastructure owner operators to what are the threshold for the pavement marking to ensure that we do not have any failure in terms of non-detection as well as false detection, or more importantly, any disengagement of the AV. Now, one important thing is that we looked into, and you can go to the next slide, was the LiDAR. LiDAR, we have another study that basically we have conducted, and the LiDAR is basically a intensity specifically can be used to evaluate the retroreflectivity. Currently, most infrastructure owner operator are focusing on retroreflectivity. This is the FHWA requirement, which is basically for night vision. And again, this is for human driving during to ensure that human driver will be able to see the pavement marking during the night. So basically, this is for the night vision or night visibility of your pavement marking. So the retroreflectivity is, again, without going into detail, but we have developed a model in here to capture basically based on the intensity to be able to locate where the pavement marking is, and then basically to correlate it to the retroreflectivity. Again, here we focused on the intensity because we have found that we have an excellent correlation with retroreflectivity. So what we wanted to do is looking at for the locations where we have a failure, whether it is a disengagement, a no detection, or basically a false detection, if we see differences in terms of the intensity when disengagement or a failure happened compared to basically a non-failure case. If you can go to the next slide. So what we have found is that, as you can see, that at 95%, there was really no difference. The more important thing is that in some cases we're seeing, as you can see from the p-value, which is, if you subtract 1 from that, this can tell you the probability. It is almost that there was really no difference between the intensity values where we had of the pavement marking, where we had a disengagement to no disengagement or no failure. And this is basically indicating that the LiDAR alone might not be a good, or basically retroreflectivity alone might not really be a good measurement to evaluate basically the pavement marking contrast, and to ensure, in case basically to ensure that we have a safe driving and operation of AVs. So basically, this is one of the things that we have. Now, if you go to the next slide, please. So in here, what we looked into is the crack sealant. And as I said, we had a lot of cases where we had crack sealant, transverse, longitudinal. And basically, what we noticed is, at least for all the cases that we have, there was not any confusion or any cases where the crack sealant had caused any problem in terms of the level 3 operation of the vehicle that we were using. And basically, this I think still the recommendation is to make sure that we have a good contrast between the crack sealant and the pavement marking, and making sure that the basically color of the crack sealant is it's might be normal, and do not like unusual basically crack sealant might be a cause of disengagement there. Now, the other important thing, if you can go to the next slide, please, was the potholes. Through driving, we noticed that basically the vehicle, the test vehicle at the level 3 full self-driving mode, it did not slow down at any potholes. So we did several tests with roads that have potholes. We looked at potholes that are classified basically based on the FHWA to be severe. And basically we had ones that were over 3 inches, basically, which is considered to be severe potholes in terms of depth. Again, different sizes. And basically, two things is that the vehicle did not avoid, but the more importantly is that it did not change the speed or slow down. And again, that might have a risk on the vehicle itself, but also currently or in the future, we still have that mixed basically traffic with automated and human driving, and basically that might also be cause risky driving, which again might cause accident in the future. So therefore, this is one of the things why we have recommended that there need to be a better I would say a pothole maintenance management, a plan and program for the different IOOs. And one of the things is there need to be an active basically program for detecting the potholes. Currently, it's more reactive, meaning that people are reporting the potholes rather than the IOOs detecting that. And again, the problem, as everyone knows, is that the potholes can occur quickly, and again, it might be very difficult for IOOs at the current time to manually detect the potholes and repair them, again, specifically during the winter. Now, if we go to the next slide, there were another issue that we have noticed, which is at the rear road crossing. Basically, in all cases, the test vehicle at full self-driving mode did not really slow down, while at the same crossroad, which had been deteriorated, basically we had a human driver would have went to a speed of less than 20 miles per hour, but the vehicle basically continued at normal speed, and basically that might also be a cause of basically danger. So this is an indication that there might be, I think, two solutions there. One is making sure that all those railroad crossings are in a good shape, which is might be hard, or there need to be a notification by the OOs basically to the AVs about the condition of those railroad crossing, and basically through I2V communication. So with that, I think that we have the recommendation, and this is the next slide. We have the following recommendation, and again, this is the first is for the pavement marking quality thresholds. Basically, for yellow center line, we are recommending basically a delta E of 11 or greater. The Michelin contrast at least 0.06, and then RMS texture should be below 0.14. Then the other important thing is the white edge line. We need it to be at least 6.6. And for the Michelin contrast, it should be at least 0.06, and the RMS should be below 0.22. We are seeing that using retroreflectivity alone for evaluating the pavement marking might not be basically good enough to ensure safe driving of AVs at a basically different levels. And this, I think, also might be applied to a level 2. Again, all of what I have presented is level 3, but level 2 will have the same thing. If you go to the next slide. In terms of potholes and a crack sealant, as I said, the crack sealant, we did not really see an effect on the AV safe operation, but for the potholes, we're seeing that it seems it's not slowing down and it is not detecting it, and basically, therefore, there should be a good roadway maintenance program by IOOs to ensure that we do not have basically at least large potholes that might cause risk again to AVs and basically to human driving vehicles. The other thing is also there should be for railroad crossing a notification because we have noticed that basically for deteriorated railroad crossing, basically there were issues of the full the test vehicle at full self-driving basically mode. There was a failure there, and basically there should be a notification to the AV of the basically how good or bad is the railroad crossing, and basically the condition for that railroad crossing. With that, I will turn it into Muhammad, and thank you.
All right, so I'm going to shift into human factors, interaction with AV, and perhaps I'm going to start with the variability and the approaches, safety approaches, in particular with OEMs, from multi-layered safety to vision-only systems, as it can be seen in the picture. Tesla is using now only cameras, no LiDAR, no ultrasonic sensors. It's only now for hardware 9 cameras versus more than 40 different sensors from Waymo, as an example. These variations affect sensing, software and hardware update frequency, and driver interaction with such evolving systems. While infrastructure must adapt to mixed system reliability and performance, our NCHRP simulator studies assess how drivers interacted with level 2 and level 3 automation for certain scenarios. Findings will guide infrastructure designs that enhance safety, trust, and consistency. Next slide. Another reason why human factors are also critical and needed, looking at recent data and investigations by the National Highway Traffic Safety Administration over the past year and this year, reveal also the critical human factors element in researching how human drivers and human users are interacting with automated vehicles. Open probes now cover millions of vehicles due to automation errors in fog, glare, and other challenging conditions. Waymo, for instance, issued a recall to correct barrier detection software. Tesla investigations also raised concerns about delayed crash reporting and rule-violating behaviors like red light and stop sign running and lane incursions. These real-world issues emphasize the need to understand how drivers and automation interact and how infrastructure can help reduce such risks. Our UC field testing, as demonstrated by Munir, utilizing FSD 12, version 12 and hardware 3. We also extended this work, and we did about 1,600 miles of drive utilizing the recent publicly available FSD 13.2.9 with hardware 4. This has basically revealed more issues, even there are some improvements, but generally speaking, when we think about FSD in particular, and we can identify different issues, including like FSD from park, illogical navigation out of parking lots, illegal U-turn sometimes, maximum speed offset that actually recommended by Tesla itself to be plus 40% above speed limit just to match traffic flow. Sometimes, yes, we understand speed variability is a big issue in traffic safety, but going up to 40% above the speed limit, Tesla FSD right now for this recent software update is speeding most of the time, specifically when you think about the different full self-driving modes. In hurry mode specifically, you can see that Tesla is always occupying the most left lane, and it does multiple lane changes in that particular mode with a lot of speedings as well. I'm not going to go over the different issues that we have experienced with our observations from the field testing. You can go to the next slide, but I'm going to just highlight some of these specifically related to work zone, as mentioned by Sam and by Munir, and the complexity and difficulty of detection of work zone and the complexity of the faded lane marking, among other issues, including work zone flaggers and ramp metering signals that actually FSD right now is not reacting or responding to. It is critical than ever before to understand how human drivers are utilizing level 2 and level 3 automation between autopilot, which somehow considered level 2, and FSD, which is considered level 3 automation. And also, we're keeping our eyes on the improvement with the recent release, and it's still, I think, in a beta version 14.1 that was released a couple of weeks ago. It is only available right now for influencers and early testers. We don't have access to it right now, but Tesla is promising that this is going to enhance handling closures, debris, work zones, potholes, and emergency vehicles as well. So this particular case study utilizing our UC driving simulator lab is focusing mainly on one case study that was identified by the NCHRP panelists to look specifically into work zones with flaggers in suburban environment on a two-way highway with one lane closed. Again, we have these lists. Our recent publication paper published in Accident Analysis and Prevention this year also indicated that AVs, these results actually is based on 27 AV testers in California. These data from DMV, California DMV, between 2021 and 2023. What we found is object perception, detection, and prediction issues accounted for 46% of this engagement. Additional and other studies, in addition to our UC initial results and observations from the field study, also showed a wide spectrum between people trusting automated systems versus driving in a very conservative fashion when it comes to using FSD among other systems. This is also according to a recent study utilizing an online survey for 103 Tesla FSD users. So the objective of this case study specifically is to understand and to, if you can go back to previous one, to understand how automation disengagement can guide infrastructure owners and operators and OEMs to improve safety of ADS. Here, this is one of the recent FSD 13.2.9 hardware for in a construction zone. There are two issues here. First, it selected the most right lane, the right turn lane to go straight, and after actually approaching the intersection and the signal, it tried to squeeze back in full self-driving. I would have disengaged early on if that it was not actually for this particular study, but I waited to see how FSD 13.2.9 can actually react and correct for such violation to start with by selecting the wrong lane from the beginning at the work zone. Next slide. Here, specifically related to our case study, we can see the progression that FSD has made from version 11, which usually FSD actually reacted to a flagger with a stop sign as if it is an stop sign at an intersection. So it will wait just like for a few seconds and it will continue regardless there is someone is holding the sign in the middle of the road. This was actually improved in version 12. And in this particular one, Tesla disengaged the full self-driving when it saw the stop sign, but after that, the driver tried to re-engage, and actually Tesla was trying to make multiple attempts to continue behind the flagger once it was switched to slow. However, it did not happen until it was actually switched to slow. Another video on the right is showing this engagement, again, responding to a construction zone flagger. However, in the recent FSD version, the FSD system did not recognize the slow and it did not continue, and the driver had to take over the driving manually. Next slide. Another very interesting interaction with a flagger at the work zone. Tesla made a right turn here, and actually it just overtook cars waiting for the flagger with a stop sign, and the driver had to back behind these cars again. But the car actually detected the stop sign and stopped. Next slide. So the main task of this one is to see how infrastructure modification digitally and physically could actually improve and enhance the engagement and disengagement early on prior to work zone with a flagger with a stop sign. Next slide. In our case study one, we designed 18 distinct scenarios. We had a baseline testing level 2 and level 3 without takeover requests. This was actually introduced in clear and moderate rain. And also we have a misinterpretation scenario where Tesla approached the flagger and then it continued as if it misinterpreted the stop sign with the flagger. And then we have the infrastructure modifications, again for level 2 automation and level 3 with physical and digital infrastructure modifications. Next slide. These are the different roadway scenes that we designed. We designed 2 scenes, 2 tangents, one on a straight segment, and another one is a straight segment post horizontal curve. This is for learning effect to randomize the different scenarios for level 2 and level 3 automation. So again, the baseline, we had no modification. We did not have any additional signs digitally or physically other than what was actually provided in the NUTCD. And then we had 2 different, 3 in general modifications. Modification number 1 was physical road sign placed at 200 feet upstream of the first work zone sign. Physical road sign 350 feet upstream of first work zone sign. And then we have digital in-vehicle message that was placed similar to modification number 1 with a physical road side sign at 200 feet, because we usually, when we have an in-vehicle warning, this doesn't need to be like far away from the critical zone that we would like to provide a warning for. Next slide. So this is a much bigger picture just to see. We introduced this physical sign saying work zone, no automation. So basically, we're trying to encourage drivers to turn off their or disengage their full self-driving or autopilot or level 2 and level 3 automation early on prior to the work zone in case that they were distracted with a secondary driving task by testing physical sign one time and testing a HUD or a head-up display work zone, no automation another time. Next slide. We started this experiment by inviting 7 subject matter experts. Those are transportation professionals with some experience with automated vehicles at level 2 and level 3. They provided some input and feedback to update those scenarios for the driving. Next slide. This is the invitation, and I'd like here just to touch on one aspect for the inclusion criteria, generally speaking. One of those inclusion criteria was we need drivers, obviously, with prior basic familiarity with adaptive cruise control, partial automation. We invited 15 participants in total so far for case study 1. We invited additional participants. They are not included in the results for this presentation. However, later, after the rapid evolution of the FSD, and we've seen like a lot of users now and subscribers for FSD based on like crowdsource and X and some data from Tesla specifically, that FSD is getting much better now and there are more subscribers. we decided to update the inclusion criterion for the cruise control, adaptive cruise control, and L2 partial automation experience to only include Tesla drivers with full self-driving active subscription and experience. Next slide. For our study, we started obviously by introducing the driving simulator to our participants. We also did some eye tracking gaze calibration. We had multiple warm-up scenarios, and then we started the actual experiment for L2 and L3. Again, it was randomized for the learning effect with and without the infrastructure, digitally and physical infrastructure modifications. Next slide. This is just an example of one of the participants driving an L2 with M1 scenario where the sign was located at 200 feet prior to the work zone first sign. And as you can see, this could be actually engaged by just using the steering wheel buttons to engage level 2 automation, which mainly adaptive cruise control and lane centering. And we can see the engagement of the system at the beginning and then the disengagement breaking when the sign was actually seen. And we see the re-engagement after the work zone and the flagger as well. We can see the re-engagement again. The participant actually re-engaged by pressing the button one more time after the work zone. Next slide. This shows the other way for autopilot. We have a dedicated button for autopilot, similar to what FSD in a Tesla or other cars that you can actually initiate. This is a supervised, hands-free. So drivers, we've seen both. Some drivers actually had their hands on the steering wheel, but mostly we had other participants with their hands actually on the lap, not on the steering wheel. And they engaged and disengaged, but the majority disengaged, as I'm going to show in a later slide, and then the engagement happened after the work zone. Next slide. So this is just the demographics for our 13 participants for case study number 1. The majority were between 25 and 34 years old and male-dominated participation. And as I mentioned, we used both the sim observer data collected related to lane position keeping and those speed profiles, in particular engagement, disengagements, events, as well as some eye tracking data, gaze allocation specifically of the different area of interest. Next slide. So this figure specifically is showing level 2 automation with this engagement. And as you can see, it varied. We're providing here the min and max when this engagement, manual disengagement happens for baseline scenario and the center line type, digital modification in blue line, and physical modification green, and physical modification 2 with the sign at 350 feet away from the first work zone sign in purple. You can see that the best performance basically, or the maximum distance, or we can say the early disengagement, manual disengagement event happened when they have seen the sign for work zone, no automation. So some of the driver decided early on just to manually disengage. I would say that 100% for all drivers disengaged manually prior to the actual work zone and where the flagger is. But you can see clearly in this that with the infrastructure modification physically and digitally, we had the earlier and more advanced disengagements happened during or for those infrastructure modifications. And for the baseline, it's usually happened at the very late at the work zone prior to the flagger themselves. And we can see also the re-engagement happened as it was seen in the video after the work zone itself. And here, this actually is showing the eye tracking gaze data specifically. The concentration means where during those engagement, disengagement, where drivers were actually looking. And we can see in the baseline, it's somehow scattered between the roadway and the side of the roadway. We can see also for physical modification 1 and 2, where there were more of these signs on the right. There are also some gaze between the roadway itself, the center of the center channel, And the side of the roadway, there are some glances to the side of the roadway, which is expected. However, for the HUD, specifically the digital modification, we can see the majority of the concentration of the gaze is in the roadway, where also the head-up display with the warning message came on the screen. Next slide. This is for level 3 automation, and we can see perhaps a distinct difference between L2 and L3, and this is perhaps could be related to the expectation of L2 and L3. Next slide, yes. We can see concentrated clusters for the min and max. So basically, this is telling us that participants split into two major categories: those early disengagement adopters, where they actually decided just to disengage the system early on once they saw the digital or the physical infrastructure modification with the sign asking them for no automation. And then we see another group of participants where they decided just to do it later when they saw also the flagger sign and just prior to the work zone itself, the active work zone area. We can also see here that digital modification in both L2 and L3, we had this abrupt response to the warning when it came, because the modality used for this was both visual and audible, and that's why it triggered more abrupt response to disengage and brake, and this is actually is noticeable in the speed profiles for the different infrastructure modifications presented on this slide. Next slide. Very similar for the gaze was also expected, and we got very similar results for the gaze concentration and glances on the physical and digital infrastructure modifications. And mostly the difference here were statistically insignificant when it comes to adding this, which basically can tell us that we did not introduce additional distraction by providing either the physical or the digital infrastructure modifications. Next slide. We followed this by a post-survey where we asked questions with respect to the cognitive workload, and as expected, the level 3 had the lowest cognitive workload on drivers while driving this particular one. As expected, some of them actually expected that level 3 can perhaps handle work zone to some extent, but obviously for level 2, everyone understood that the car cannot actually handle work zones in particular, and they would need to just disengage the system prior to the work zone. The comfort also, we can see that the comfort for physical and digital infrastructure, the comfort and familiarity with the physical infrastructure modification, the added sign or the new introduced sign received 7 out of 10 versus digital just received a moderate, which basically 5 out of 10. Also, as part of an open-ended question in the post-survey, 77% of the participants preferred the more familiar road sign on the side of the roadway, not the in-vehicle message. They also complained a little bit about it was a little bit abrupt with the audible and visual. This could be also improved, but this is out of our hand. This is going to be done by infrastructure to vehicle communication, and the modality could be actually tuned by the OEMs themselves. Next slide. I'd like here just to touch a little bit on the latest beta version of FSD 14.1 with hardware 4. As you can see in this one, the performance has improved quite a bit. You can see in this scenario specifically, the FSD system detected the stop sign and also the slow, and seamlessly the FSD system moved or converted from like slowing down, approaching the stop sign, and upon or the onset of the showing the slow sign, even though it was not actually provided in the visual display on the car itself, it still showed a stop sign. The car continued and increased the speed, and it changed lane to the opposite direction. Next slide. We have another example here with 2 flaggers basically in this one. And as you can see, in the first one, it was detected as a stop sign. The car reduced the speed almost to 0. It's close to 3 miles per hour, but it's almost, you can see it's almost 0. And then once it's switched to slow, the car actually started right away, seamlessly moving to the opposite direction and continue and increasing the speed. And now you can see actually another flagger with a slow speed, even though it's going to be shown as stop, it's not stop, it's slow if you look up on the video. And the car actually continued through while seeing the flagger with. So there is actually a very significant improvement when it comes to dealing with flagger. However, before I actually go through the conclusion for the case study one, I'd like just to highlight why this is still needed. I'd like just to touch on with not only the variability in the system and the rapid evolution of those FSD systems. I'd like to mention that not every single FSD subscribers or owners, because there are two models, you can either purchase the FSD from the very beginning or you can subscribe to it. We will see still a lot of variability and variation between FSD systems on our roadways. I'd like to mention that older Teslas with FSD hardware 3 specifically and prior hardware will not be able to receive those newer updates. So 14.1 is not going to be released for everyone. This is only for hardware 4 with the 9 cameras and no ultrasonic sensors, among other sensors. So basically, what we can tell here from FSD version 11, 12, 13, and 14, we will see all of these different subscribers. Yes, we understand that not all of them will see more subscribers and users for recent releases because actually it improved quite a bit than what we're going to see for older hardware and software versions. But still, this wide variability between those different safety approaches when it comes to strategies, when it comes to FSD implementation, we can see that we still need those infrastructure digitally and physically to communicate with users of those level 2 and level 3 automation as well. So with this, the conclusion here, we can see that both physical and digital modifications improve driver awareness about the those flaggers and work zones in particular, and their takeover was much earlier than the baseline with no physical or digital infrastructure modifications. The physical infrastructure modification with 300 feet sign away from the first sign at the work zone had the earliest braking onset, longest braking distance, smoothest deceleration disengagement in both automation modes, L2 and L3. Next slide. When it comes to visual attention, as I mentioned, we don't have any surprising results from this. Actually, both digital and physical infrastructure modification did not add any additional distraction to drivers using L2 and L3 automation. And as mentioned, 77% preferred physical signs due to familiarity with the sign. Our second case study is focusing mainly on interaction between vulnerable road users, bicyclists in particular, and AV. And I'm not going through the statistics provided on this screen, but I'm going just to highlight one thing, that cyclists, it works both ways from the AV user perspective as well as from cyclist perspective. Various studies actually showing low trust in sharing lanes with an AV. And some studies actually suggested that there should be some communication that AV can relate to those users, that there's an AV, yes, I see you on the roadway, I'm reacting and I'm giving you more space, and vice versa also. AV users should be notified by the infrastructure about the presence of pedestrian and bicyclists on the roadway, which I2V and V2X could also be used for those such communication. And this particular case study is focusing on this particular aspect. Next slide. While we can also see that Waymo and Tesla recently passed the vulnerable road user interaction test with 89% according to IIHS, and then the model of Waymo actually stating that injury crash reductions versus humans, the comparison between human drivers and their system resulted in about 92% in reduction in pedestrian crashes and interaction or critical safety events, and 82% for cyclists. And I do have some also videos about how Tesla, next slide, is reacting to bicyclists, detecting them very early on. You can see the bicyclist before on the screen, before even on, you can see it from the windshield. You will see also that the recent 14.1, the beta version available only for testers, early testers, You can see it's given more space even in a very narrow roadway with no marking, and Tesla's giving more space. We have another example, next slide, showing also on another roadway type with no shoulder that Tesla is actually crossed over the center line just to give more space to the bicyclist. Next slide. Another example here, and more like suburban settings. You can see it's very crowded. We have parked cars on the side, no space for bicyclists. Tesla's navigating between the giving more space to the bicyclist while also making sure that it's giving more enough space for the oncoming traffic. So it seems like there are a lot of improvements. However, we still would like to assess from both, and again for older systems and for both our AV users as well as from bicyclist perspective. This is where we're actually going with the second case study, driving simulator study. Next slide. And here I'm just listing additional statistics about the fatalities related or involving vulnerable road users, which account for about 50%. And the coexist, which basically are different road users and different types of manual driven as well as automated vehicles with different automation levels will coexist on our roadways in the mid-term and like the immediate term and mid-term and long-term. Perhaps we can see maybe a little bit of a shift in market penetration rate when it comes to adoption of AV system and the readiness of our infrastructure. What we aim for this particular study is to see the different types of infrastructure modification while we can provide those communication between AVs and bicyclists, as well as the physical separation between bicyclists and AV or vehicles, generally speaking. Next slide. These are the tasks, very similar to the first case study. This is an ongoing, so I don't have a lot of results to share with you today. Next slide. But these are the three different environments designed so far, and we started testing with some participants. Again, this is only level 3. We're not going to focus on level 2. This is only for Tesla FSD subscribers and active subscribers for full self-driving for Tesla in particular, where again, testing both the infrastructure modification, shared lane, a bike lane, a conventional bike lane, as well as a bike lane with a physical vertical separation, in addition to digital communication between bicyclist and AV as well. Next slide. We do have an online survey that we're also conducting, and I'd like any Tesla drivers on this call or this webinar to go and scan this QR, and also the link is provided in the chat box to take this online survey with respect to issues and how FSD your system and how actually you're utilizing the system for both these case studies for work zone with flaggers. There are some general questions at the beginning, but we have a focus also to complement the two case studies for work zones as well as the interaction with vulnerable road users. With this, I'm going to turn the presentation, the webinar to Sam. Thank you, everyone.
Thank you, Dr. Ahmed and Dr. Nazal, for sharing your preliminary findings on these case studies. I'm really excited to see all of this come to life in our web resource, which brings us to this next part. Just due to time, I'm kind of going to run through this really quickly, but I will provide a link in the chat to our web resource. You can also scan the QR code if you prefer that. If we can go to the next slide. This is a really quick overview of essentially our web resource. This is a draft, so the final version will be published in May 2026. But essentially this third tab, which is our infrastructure recommendations tab, is like the primary focal point of our website. So in this format, you can see all of our infrastructure recommendations by category. You can easily click to see all the recommendations in a collapsible format. You can click to learn more, and then also an associated best practice will be in each section as well. Next slide. And so on behalf of our NCHRP research team, I'd like to thank you for taking the time to listen to our presentation today. We'd love to get your feedback through the survey. It shouldn't take longer than 5 minutes. Ultimately, your feedback will help us further refine our recommendations in our guidebook, so we can ensure that it's the most accurate and useful for those of you that will be using it. And if you prefer to take the survey from your computer, I can provide another link in the chat. So feel free to use that as well. And it looks like we are right at time. So Adam, I don't know if we will have time to answer questions. If you want to answer one, leave that up to you.
Certainly. Thank you. Thank you again, Samantha and Dr. Ahmed. And I feel like we have a couple great questions that we're going to want to let people know. We are at the time block, but if we can take just a moment to go through the ones that were answered previously. If you have any additional questions, please put them in the Q&A box, and we'll look forward to doing that. And again, what was presented on will be recorded, and so that you can share with everybody. So real quickly, if you could just address, Samantha, the how agencies might measure or monitor infrastructure condition to optimize performance, and the recommendations that that was asked about, and what your reply was.
Yeah, so in that TRB web resource, we are currently working on developing an implementation strategies section, which will be in another tab. And essentially that's more so like deployment strategies for IOOs. And so one of the sections that will be in there is essentially on conducting infrastructure readiness assessments. So I know that there are a lot of different vendors in this space which will recognize in that document, but one that just comes to mind, like I highlighted in the chat, is ESI AI. So they're an online app platform that can allow IOOs to monitor and assess their infrastructure themselves.
Thank you. Yeah, and that's the mention of ESI. Just a reminder, everybody, is FYI only, not a recommendation by the project or by anybody else, but that's great. Thank you for that. And then Dr. Nizal answered a question that was in there about are there were any other vehicles used other than Tesla or the Tesla FSD for rail crossings? And Dr. Nizal, if you want to make sure everybody, people haven't seen that answer, if you could go ahead.
Yeah, so for the NCHRP, we were looking really at the most commonly used production level vehicle with a full self-driving basically capability. And at the current time, it was Tesla. This doesn't mean that we have others, but the one that is currently most used, I would say, is basically the Tesla. And one important thing that I would say that those recommendations as will be are important really for the level 2 and level 3. And we are aware, as Dr. Ahmed have mentioned, that there are new versions of the full self-driving even for the Tesla, but those might not be applicable for basically older version of those AVs. So our focus is really for current and maybe near future. Again, things might change, and that might really why I think there will be a recommendation that all those like whatever we have in this study might need to be re-evaluated maybe in 5 years. But again, the thing is, we wanted what is currently common practice, and that's what will be applicable really in the currently and in the near future. So yeah.
And that serves as a good reminder for the links in the chat box for assisting, for whether you're a Tesla owner or want to contribute and give response back. And I thought that the four of you did a great job describing how you actually capture a rapidly changing environment like that. So just for those who maybe didn't see the beginning of the webinar, make sure to go back and look at some of the research frameworks and approach on how not only the environment has changed rapidly on a month-to-month basis through the last year, but the approach for the research project to capture it. So thank you so much to Dr. Ahmed, Dr. Nazal, Samantha Anderson, and to Kate. We really appreciate Kate Piscai, sorry. We really appreciate the presentation. The research is fantastic, and we look forward to hearing more about it as you move into your next phase. And again, reminder to everybody that a recording will be available soon, and please sign up for the NOCoE newsletter in order to receive that recording. Thank you again, everybody, and have a great day.
Thank you.
Thanks, everyone.
Thanks, Adam. Thank you, everyone.